So today we're just going to, I think we'll just start with doing 7.1, which is our next chapter. And there are 4 sections in 7.1, I believe 4. And the first one is estimating the mean when the population standard deviation sigma is known. So I want you to imagine that we have a population that is the normal in shape, right? So it's non-weird, nice little guy like that. And we are interested in finding the mean. So we're interested in finding the mean mu. So that means we're interested in finding the population mean. Well, I guess what I could do is, couldn't I just ask every single person in the population how old they are? And I suppose that's what it is. Oh, some unusual dings in here now. So we're find the population mean, right? Just by doing a census, ask everybody. Well, most of the time that's not going to work out. So what do we do instead? Well, we get a sample. A really good sample. So hopefully it's a simple random sample. That would be the best. And let's say that this sample was 100 people. There's one other thing about this one, which is a little unusual, but let's assume that we know it's true. Sigma, for somehow or other, is known. We know the population standard deviation is 10. And there might be ways that that could harm. So we found that guy. We got this fella. We get the mean, and we found out that the average age of, let's suppose this is a country, and let's say it's Scotland, just for argument's sake. So I'd like to know what the average age of people in Scotland are. And I know that the standard deviation is 10. And I take a sample of 100 Scotsmen, and they end up being that the sample mean is 35. What can I conclude? Well, if we just took what's in front of us, I could say that my best estimate is that the mean of the population is a little squiggly thing that look like the OC. That simple means is approximately 35 years old. Well, we'd like to do more than just tell you what our best estimate is. What we'd like to be able to do is to kind of give you a kind of tolerance. I mean, are we really sure it's 35? Or are we not really sure it's 35 at all? Or are we somewhere between those two? So how do we get more specificity into this? How do we say how good this estimate truly is? Well, that's pretty much what 7.1 is going to deal with. There is, in fact, a process where we can put an interval of values, and we can say within this interval, we are 80% sure the right answer for the mean is 90% or even 99%. And that's what our goal is going to be. We're going to find a guy, and it's got an interesting name, this interval. It's called a confidence interval. So for instance, a confidence interval might be 30 to 40. It could be 20 to 45, and it could be 15 to 55. These are intervals. And I might say, look, 99% sure that the right answer is somewhere in that range. I'm 90% confident that it's in this range, or maybe I'm 80% confident it's in this range. And our job really is to find what these numbers are. And they have names. At least let me find out what the book calls them. I call them upper and lower limits. And it's nice that they call it the same thing. This number here is called the lower limit of our interval. And this guy here is called the upper limit. Now, the last while we've been doing questions, we haven't really needed to do much number crunching on our own, right? Salt did a lot of it. Salt is not going to do anything for us this time. So that is means that we have to put more work into collecting the answer. So let me show you how to do one of these confidence intervals. An 80% confidence interval first. Let's just call it 80% CI for short. It's the mean of your sample, plus or minus. In this case, I've got my little list. I'll do it in red. 1.28 sigma over the square root of n. That's the formula for an 80% confidence interval. Now, in the story that I've got here, n was 100 people, the sample mean was 35, and the population standard deviation sigma was 10. So you might think, what's this weird 1.28 guy? Well, let's do this guy aside. There's a little guy called ZC. This is basically a Z-score that gives you a confidence interval of C. So if you want a confidence interval of 80%, that guy is the guy you use. And for 80%, that guy is 1.28. So every single question where you're going to do an 80% confidence interval, you're using 1.28. Now the next number is a 90% confidence interval. And if you want to do a 90% confidence interval, the magic number you use is that guy. If you want to do even more sure that you've got the right answer, like this one, you use 1.96. And if you want to be like almost guaranteed that you know where the answer is, you do the, oops, that's a 2. Use this one, 2.58. Right, so side issue, back to this one. An 80% confidence interval. Let's see what that looks like. The mean in our story was 35. Add or subtract 1.28 times 10 divided by square root of 100. Well, that ends up, because I picked numbers that are really nice to work with, 35 give or take 1.28. Now, the lower limit is what you get when you take that number away from the mean. So let's see what that looks like. So I'm going to go 35, take away 1.28. And that gets me 33.72. And then if you add that number, you get the other extreme, which is 36.28. To remind you, this guy is called your lower limit. This guy here is called your upper limit. And this number, whatever this whole package is, this is called your margin of error. So I can say I am 80% confident that the average age of Scotsmen is somewhere between 33.7 and 36.3. So do you see now I've got a range of values where I believe the right answer is, and I even can tell you a confidence, how confident I am that it's in that range. Well, I don't want to be 80% confident, because isn't there a 20% chance that I'm not right? You know, there's a 20% chance that the average age of Scotsman maybe 32 or 39. So let's look at a bigger one. Let's suppose I would like to be 99% confident. So a 99% confidence interval is X bar plus or minus. Now, if you want to be 99% confident, you use the 2.58 guy. So it's going to be 2.58 sigma over root n. In this case, 35 plus 2.58 times 10 over the square root of 100. Which means somewhere in region 32.42 all the way up to 37.58. So I can be pretty darn sure that the average age of Scottish people is in this range. Now that's much better than just saying I did a sample of 100 and it was 35. Now I can tell you I'm 99% sure that the right answer, right, the true answer, is in this range. It's quite important that you're able to do that. Let's try another one. Suppose the data this time was IQs, and I'll pick on the French. And I know that for IQs that the standard deviation is 10, because that's what it is anywhere else. And I would like to know what the average IQ of the French is. So I go and get a nice simple random sample of 40 Frenchmen. And the average IQ was 95. I'm picking on French, right? What confidence interval would you like me to calculate? 80, 90, 95, or 99? Pick one.
99.
Oh, another 99. So here we go. 99% confidence interval. X bar plus or minus 2.58. That's the magic number that you would use for a 99% confidence interval. Sigma over n. By the way, in a lot of textbooks, that is called 0.99, and then you turn it to 0, that number, but I just saved the line. 95 plus or minus 2.58 times 10 divided by the square root of 40. So that ends up being 95 plus or minus 2.58 times 10 divided by the square root of 40. And the answer I get is about 4.1, right? That number there is called the margin of error. Has anybody heard that term being used lately? Because I've heard it quite a few times on TV. Margin of error. You don't watch TV much lately. Aren't there a whole load of polls going out saying what percentage of people are going to vote Republican or Democrat and who's going to win the election? And they might come up with a number like 50% or 52%. And then they said the margin of error is 3%. or the margin of error is 2%. Or they might say it's a tie within the margin of error, right? Things like that. That's where that's coming from. It's coming from a calculation, a proportion version that's very similar to that. So let's see what the numbers look like. It could be as low as 90.9 when you take that number away from 95. And if you add it, it could be as high as that. So we're saying the average IQ of French people, French adults, is in that range. And not only that, I'm 99% confident that it's in that range. So in other words, 99 times out of 100, aren't I going to be right? This interval does contain the average IQ of, in this case, French people. It's pretty good accuracy, right? You're going to only be wrong 1 in 100 times. There is no way of making this number 100% confident, because the only way you could do that is if you actually did know everybody in the population and you asked them. I can do another one. Here's a statement. The average IQ of a Frenchman, like a French person, is more accurate, is less than 100. Why can I say that with 99% confidence that it's true? How can I use this interval to justify my statement that the average IQ of a French person is in fact less than 100? What do you know then? Maybe phrase it a different way. What do you know about all these numbers? Aren't they less than 100? Every single one of them, right? Any number between 90.9 and 99.1, that's a range, an interval. Every single one of them is less than 100. And that's the average IQ. So the average IQ, less than 100. Couldn't I also use that interval to say that I'm 99% sure that the average IQ of a Frenchman is at least 90 or better? Because all of these numbers are bigger than 90. Any questions? Try another one. Let's suppose that there was a university with lots of people in it, and I wanted to know what the average GPA of a student at that university was. And the standard deviation of the population is 0.3. And I go and I collect 2 different samples. One of them is tiny, 10 people. Now we can get away with that provided that the distribution is normal, which we'll assume it is. And I want to find a 90% confidence interval. And then I decided to go and try a little bit different. And I decided to get a sample of 400 people. Which of those 2 samples, the first one or the second one, is likely to give me better answers? I think the dog's trying to answer. Which one of those two? Sample of 10 or a sample of 400? Which one would give you a more accurate prediction?
The first one?
So asking 10 people and getting the answer is going to be more accurate than asking 400 people.
Oh, no, the second one.
Yeah. So you kind of, if you phrase it that way, your brain kind of says, oh, yeah. And that's the one. Yeah. So we are going to find this one and that one. And we're going to get the same confidence intervals. So that means apples with apples, right? We're not mixing and matching. Now, just say to make the calculations a little bit artificial, but so we can compare them. Let's say by sheer coincidence that the GPA was 3.1 in each sample. So the average GPA of the 10 people we asked was 3.1. In this case, 400, it was also 3.1. And let's see what the 90% confidence interval would look like. We'll do n equals 10 first. Well, a 90% confidence interval is going to be the mean plus or minus for a 90%. Oh, by the way, this is my little list, right? For a 90%, the magic number is 1.645. And then it's sigma over root n. So it's 3.1 plus or minus that guy times nothing 0.3 divided by the square root of 10. And let's see what we get. Well, we get, bring up a bit higher, there we go. We get 1.645 times nothing 0.3 divided by the square root of 10. And that ends up being plus or minus 0.16 to 2 decimal places. So on the small side, you're going to get 2.94. And on the higher side, you're going to get 3.26. So based on this very small sample and the assumption that it's normal, which it has to be in these questions, we're able to put a kind of range of values on where the true average GPA of people at this university is. It's somewhere between 2.94 and 3.26. Now I'm going to do the exact same calculation with one exception, 400 people. Now, if this works out, shouldn't the interval be much smaller, right? More accurate says, look, in this tiny little interval, we're 90% sure the right answer lives. So it's going to be X bar, add or subtract the magic number for 90%, sigma over it. And that's going to be 3.1, 1.645, nothing 0.3, but now the square root of 400. If we do this calculation, then we have 1.645 times 0.3 divided by the square root of 400. And we got 0.024, so we'll call that 0.02. Which means 3.08 to 3.12. Can you see that this is much tighter? There's not a lot of difference between the biggest and the smallest. And we are 90% sure that the university's GPA is in this range. Compare it to this one, isn't this much broader? Now, the number that kind of tells you how spread out, how big the results are, is this guy here, the guy I called the margin of error. You can see in this case, the margin of error is 0.16, and here it's what, 8 times smaller at 0.02. So what does that tell us? Big, whoops, oh, I have two G's in big. Big sample size. Small. E. E is the letter we use for margin of error. So small margin of error. The reverse is also true. A small sample size gives you a big margin of error. Now, this process of creating confidence intervals is very powerful. If we know what sigma is and we know that the distribution is normal in shape, it looks like a hill, we can take our sample, whatever size sample we happen to decide to use, and we can create confidence intervals based on it. And not only can we do confidence intervals, we can even choose what kind of confidence interval. Right, I want to be 99% sure. I want to be 90% sure. Here's actually the choices. 80% confidence, 90, 95, and theoretically even 99. And by that, we are able to create these confidence intervals, which in this case is that one, right?
Can I see that paper that you just showed us one more time, please?
Yes, this guy here has this, the ZCs. The ZCs are these magic numbers that go here, depending on what confidence interval you're trying to generate. So it's one of these four in every situation. That means I can save a lot of money and still get pretty good answers. You know, do I want to know how many people are not looking for a job? Now, that's not the same as unemployed. Some unemployed people are looking for a job, and some unemployed people have given up. They're just not going to bother, right? They've just lost hope or whatever. Now, you can simply just take a random sample of 200 people who don't have a job, and you can figure out how many of them are looking for a job because you asked them. And you could create a confidence interval based on that type of information. I could do a confidence interval based on anything, provided I make two assumptions: that the population is normally distributed and that I know what sigma is. If I got those two things in the bag, I can do anything any confidence interval I would like. So let's think another one with some numbers in it. I got my internet here. Let's see if we can get some real data. Right. Anything you're interested in that's got a number associated to it. Anything you'd like to know, and we could do a confidence interval based on it. You're not interested in finding anything? Okay, I'll do one. In United States of America, let's find the average number of children in a family. And I am going to look at what sigma is. So
we can't see the screen you're drawing on.
can you see the white piece of paper?
No.
Oh, sorry. Okay, let me type in this first. And then I shall do it for you. So here we go. Suppose we're interested in the average number of children in a family. And I've just gone looking for what sigma is. And the answer is 1.5. Okay, now we need to do a sample. Well, we have got one of the smallest samples in the world because the class is pretty small. And there's 5 of us. 1, 2, 3, 4, 5. Oh, we could probably get 2 sets of data out of this for some of you. Right. I kind of need you to be taking part in this. You, of course, are always allowed to not take part if you feel uncomfortable about sharing information, and totally cool with that. But if you do want to take part, first thing we're going to get is how many children are you a member of? So in your family, how many you are? And I'm 10. Anybody else want to count brothers and sisters and themselves?
There's 3 in my family.
Okay, anybody else?
I'm an only child.
Okay, anybody else? Okay. Second kind of family, do you know you could have your own kids? I don't really know anything about you because I see blank and I'm not even sure what your ages are. Does any of you have a number of children? And we could use that as data because right now I've only got 3 numbers and it's pretty scarce. Like I have 2 kids, so that would be a 2-child family. Or I have 1 kid and that's a 1-child family. Okay, that could happen. Do any of you, oh, thank you. Do any of you have siblings who have families? So I got a brother with 2 kids, or I've got a sister with 3 kids. If any of you get that kind of number, we could share. I'm trying to get at least up to about 6 or 7. Courtney? You went yellow, which normally means you're about to say something. Okay, I'll put 1 in. My brother Billy has 3 children. And my sister Pearl has 7 children. My sister Morik has 4. Sister Mary has 3. There, we got enough there. So, okay, not all of them are Americans, but too late now. 1, 2, 3, 4, 5, 6, 7, 8. So I get a sample size of 8. And I'm going to use that to try and do a confidence interval on the average number of children in an American family. So to get the mean, I basically just add everything up and divide by 8. So that shouldn't take me too long. So 10, add 3, add 1, add 2, add 3, add 7, add 4, add 3, and I get 33. And that ends up being 4.125. So let's just call that 4.1. Okay, I'm going to go for, let me switch over now so you can see what we're doing. Maybe you already have. Right, I'm going to switch over now and pick a confidence interval based on this fella and that sigma. So I want a 95% confidence interval. So it's going to be X bar plus or minus 1.96 sigma over the square root of n. So it's going to be 4.1, 1.96 times 1.5 over the square root of 8. Here we go. 1.96 times 1.5 divided by the square root of 8. And I'm looking at 1.03. So let's just call that 1.0. Which means somewhere between 3.1 and 5.1. And I am 95% confident that the average number of children in an American family is somewhere between 3.1 and 5.1, right? Now, I know I had to use some Scottish family data, but let's just make the assumption that there's not a heck of a lot of difference. And let's put in USA, average number of children. Oh, perfect. There's a match. I should switch over so you can actually see what I was typing there, shouldn't I? Okay. Almost ready. Right. Now, the correct answer was 2.4. Pretty miserable failure, would you agree? But we can learn from failures. I can think of two major problems that caused this. What's the first one?
Small sample size.
Yeah, every time. Can you imagine I did the sample size of 2 people, especially me, right? And my sister Pearl. If I took those 2 numbers out, which since I've got time, let's do that. I put the wrong one out, didn't I? There's a 3 here. Let's see what it now looks like. Well, I have a sample size of 6. Oh, by the way, the second problem was outliers. 10 is a pretty bad outlier. Agreed, considering the rest of the data. And I'm including my sister with 7 as another outlier. So I can't really fix the small sample size. In fact, in a way, I've made the small sample size even smaller. But can I at least fix the outliers, right? So let's see what that looks like. Well, if you get the mean of this sample, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 16, 2, 4, 6, over 6, that's about 2.67. And let's do another 95% confidence interval. So it's going to be that guy, this fella, sigma over root n. And this guy is now I guess I should call that 2.7. 2.7, give or take 1.96, 1.5 square root of 6. So 2.7, let's do the calculation. 1.96 times 1.5 divided by the square root of 6. And I get a margin of error of give or take 1.2, which means it's somewhere between 1.5 and 3.9, which is really good because isn't 2.4 actually in that interval? Now, technically speaking, that confidence interval that I did earlier, I should jump back, I'm not quite sure what part we're showing right now. Not that one, go away. Right, this is the new data, right, where I took out the 2 outliers, which I considered outliers, the new mean, calculation in 95% is this. The real answer is 2.4, pretty good match. This is what it looked like with the outliers. The outliers were originally a 10 and a 7. They were here and here. What that is showing us, when you are collecting data to do one of these confidence intervals, shouldn't you be on the lookout for outliers? Agreed? Now, I eyeballed it. I said 10 and 7, but there are better ways of doing it rather than me just doing a judgment call. Couldn't I find the z-scores of all of these? What kind of z-score would be considered a potential outlier, and then maybe I should ignore it in my data? What kind of z-score should you expect an outlier to be bigger than?
Three or -3.
Yeah, that's what I was looking for. So I'm not doing it because it would take too long, but couldn't I find the mean and standard deviation and then get a z-score for these guys? And that guy might have a z-score of 4.1, and that one might have a z-score of 3.1, and that justifies my reasoning for kicking them out. So sample size, too small. In both cases, that's even smaller, but isn't that smaller with better data, for want of a better word? Smaller by sure, right? But the numbers don't have any weird outliers in them. Any questions? We're good. I like to see good. So I am going to show you some homework questions now. I wonder if I make that bigger, if the writing will scroll. Oh, good. All right. Here is our first story. Evidently, there's a particular subgroup, subspecies of hummingbird called Allen's hummingbird. Never heard of them, but here's its Latin name. And they've been studied by a zoologist, Bill Arthur. So it's real data. And suppose a small group of 18 of these being under study in Arizona. And the average weight of these birds, I'm writing this data down because it's going to disappear in a little while. The average weight of these birds is 3.15. So evidently, he catches them, he weighs them, and then he releases them. And based on previous studies, he's also found that the standard deviation of weights in these birds is 0.28, and all the units are in grams. So, you know what 3 grams weighs? I mean, these little hummingbirds are very tiny and very light, right? So they almost look like big bees, you know, they're that tiny. So we're assuming that they are normal, which is perfectly correct because you can't do this unless it is, and that we know sigma. So we are good to go. It says here, find an 80% confidence interval. So question A is going to be an 80% confidence interval. So let's kick out of this question and look at the number crunching. Okay, let's put some poor soul in this spot. What's the formula I'm going to use? Say it out loud. Or type it, I guess. Hopefully you've got audio.
Isn't it x bar plus or minus 1.28 times sigma over the square root of the number?
Yes. And I forgot to tell you here, or at least I forgot to write it down, but his sample was 18 hummingbirds, right? You know, sometimes you can't afford a big sample. You can imagine these hummingbirds are probably very hard to catch, and there might not be that many of them as well, right? They could be quite rare, and there might only be 2 or 3 in a square mile. So can you imagine if you wanted to get a sample size of 1,000, you'd probably spend half your life just catching them. So sometimes you can't help tiny samples. You just got to live with that fact, right? I just can't do anything about it. That's as good as it gets. Now, in this case, the mean is 3.15, add 1.28, which, by the way, is the magic number for 80%, right? And the sigma is 0.28 over the square root of 18. And that's going to get me this guy, plus or minus the margin of error, E. So 1.28 times 0.28, all divided by the square root of 18. And I get 0.08, at least to 2 decimal places. Just to remind you again, that bit there, that guy there, is called the margin of error. It's also, we also use the letter E for it. So if a question says, what is capital E equal to, you're going to write 0.08 in this case. Now, you go either side of this, and the way the book wants you to do it is by boxes. So you're going to have a lower limit, you're going to have an upper limit, and then you're going to have margin of error. Well, if you take that away from that, you get 3.07. If you take that and you add that, you get 3.23, and the margin of error is 0.08. And that is the answer to A. Now, me personally, I would like to do the information written like that. So I can tell you some things just based on that interval, apart from the fact I'm 80% sure the right answer is in there. Isn't this good evidence that the average weight of one of these Allen hummingbirds is bigger than 3 grams? And the reason I know it's bigger than 3 grams is, isn't everybody in that interval bigger than 3? At the other extreme, couldn't I also say that this interval is evidence to show that the average weight of these hummingbirds is less than 3.3, which is basically because everything is smaller than that. Any questions about how you took the information and created the upper and lower limits? I'm assuming we're good on that. We are good. Thanks for the thumbs up. So let's continue with this question and see what else they have in store. So in this case, that would be 3.07. This guy would be 3.23. Oh, good. I just realized I should have checked. It's to 2 decimal places, which is exactly what I was doing, so that's good. Now, it says, what conditions are necessary for us to be able to do this? 2 of the things mentioned in this list have to be true for us to be able to do this entire process. Can you look at this list and tell me what 2 have to be true? You know, I'm going to be retiring in 5 years. I'd like this class to be over before then. Go for it. Which one of those 5, even if you're not 100% sure, what do you think must be true? And if you get it wrong, you get it wrong. I think, Valeria, if you're trying to speak, it's not coming through.
Is it the third one?
Yep. Well done. Sigma is none. And the other one, which I have mentioned, has to be normal. Now, it's nice and really great and brilliant that n is large, but sometimes it's not. And even if it's not, and would you agree in this case 18 is not large, you can still do it. So these are what are necessary, not desirable, but you have to have them. They are necessary. And that's the only 2. And that's the sentence for this one. So far, so good. Now, let's turn this question on its head. Suppose I would like to know how big a sample I need. So this is the question. How large a sample do you need in order for the margin of error to be 0.02. So they're asking us to find out what n has to be in order for the margin of error to be that number. Well, the good news is there is a calculation for it. And the calculation is n, the sample size that you need, is in general ZC sigma over the margin of error all squared. Now, ZC is just a code. If you're doing an 80% confidence interval, ZC is 1.28. If it's a 99% confidence interval, it's that. So this question would have to have that as part of the question. So I guess how large a sample do you need in order for the margin of error to be 0.02 in a, say, 95% confidence interval? Well, let's see what that would look like. A 95% is 1.96. The sigma in this story was 0.28. And the margin of error that you want to get is 0.02. And then the whole thing gets squared. Now, if you want an 80% confidence interval in that same story, just change this to 80%. Won't this become 1.28? If this was a 99%, won't this digit, that's the only one you change, won't that become 2.58? So in the one that we've set up, see if I can do this in one go, a bracket, 1.96 times 0.28 divided by 0.02 brackets, and then square everything. And the answer comes out like this guy. There's a rule about what n is. Since n is how many people are going to be in your sample, does it not make sense that you would want n to always be a whole number? Now, in this particular case, does it also seem reasonable that you would round it up to 753? All makes sense. Can you imagine a different question, right? Maybe a different confidence interval or whatever it might be. And the n came out to be 141.2. Some other stuff, right? What will I round it off to? Well, you might think you round off to the nearest whole number, but that is not actually what you do. This is a little sneaky thing you have to do. Can you give me a reason why you always round up? Regardless if that's 0.01, you still make it 142.
Because the number that you get is like the bare minimum for it to work. So if you round it down, you're just kind of screwing yourself over.
Yeah, you're just shaving it off so you're not quite 99% sure. You're like 98.8% sure, and that's not where you're asked to be. So yeah, it's pretty much it. So when you do this calculation, right? So it's just basically another formula that you have to write down and remember, or at least write down and know where to find. That guy. Are you comfortable about why I've generically done it so that any one of 4 questions could be asked? So that ZC is just a placeholder for one of these 4 numbers. And in the story, maybe the next time it's a 90% that you're doing this on. So what sample size do you need in a 90% confidence interval? Well, you would plug in 1.645 here and so forth. Are we good on that? Any questions? Good. You're making my life so easy, Valeria. Thumbs up is a helpful thing. You know, thumbs down is allowed when you're not happy. So I'm going to return back to the homework. I can't tell you why they seem to be interested in these hummingbirds, but there seems to be an awful lot of the questions involving them. So question 7 is basically a rerun of question 6. Oh, with one exception. They gave us a list of formulas. Pretty much the same that I did, only I called my guy ZC and they're calling their guy Z sigma. I think ZC is better, in my own opinion. So which one of these 4 is actually the same guy as I wrote down? We just saw it maybe a few minutes ago. Which one of these 4 is the guy?
The first one?
Yes. And I'm definitely getting deja vu here. Question 8 is another story. I think what they're basically doing is just giving you practice at doing this entire process. I wish they hadn't done hummingbirds every single time. It would be nice just to do something else. And good news is question 10 is something else. It's going to be the same story, but it's just a new, a new context. Right, for the nursing medical people, here's looks to me like a medical story. Overproduction of uric acid in the body can be an indication of cell breakdown. This may be an advanced indication of illness such as gout, leukemia, lymphoma, don't like that. Over a period of months, an adult male patient has taken 7 blood tests to test how much uric acid they have got. Are any of you in the medical field actually could say, yep, I've read that, that's what they do? Does that look normal thing that sometimes gets done? Maybe I don't have a sample of nurses, that's possible. So the mean concentration, so I better write that down. was 5.45. He only done it 7 times, so the sample size is tiny, but it's 7. And its sigma is 1.79. So that's the package. A sample of 7, the mean of which was 5.45, and sigma, the standard deviation, was 1.79. And we are going to find a 95% confidence interval. So X bar plus or minus a 95%er is going to be 1.96. Sigma over root n, 5.45, add or subtract, 1.96, 1.79, square root of 7. Bring this guy into the story, 1.96 times 1.79 divided by square root of 7. And I'm looking at plus or minus 1.33. And that's going to give me a lower limit, an upper limit, and a margin of error. Well, if you take that away from that, you get 4.12. And that you get 6.78. And the margin of error is this number. So we are 95% sure that the average level of uric acid in this particular person is somewhere in the range 4.2 to 6.78. We okay with that, how that was created? So far, so good. Right. Let's try and make some mileage out of this. I have no idea what a bad uric level is, but can we pretend it's greater than or equal to 4? Wouldn't this person's average, at least we're 95% confident that his average is bigger than 4. And so this person has got issues and they should spend more time on it. Suppose it has to be greater than or equal to 8 before they're worried. Is it in this guy's uric acid level, the average value, quite safe? Isn't it less than this number? So whatever the medical field has decided is a good or bad average for uric acid, we know what his is, and then we can compare it against that number. And if it's too big or too little, then we've got an issue. If it's in the range that's not a problem, then as far as we can tell, he doesn't have an issue with the uric acid levels. Are we good? Okay, same story. I would like a margin of error, that's what E is called, of 1.00. 95%, all that good stuff. So N is equal to the magic number for 95% times sigma all over E squared. So that's going to be 1.96 times 1.79 all over 1 squared. So here goes 1.96 times 1.79 divided by 1 doesn't do anything. Squaring it, and I am looking at 12.3 and some stuff. Well, what that tells us is that if you want to make sure that your margin of error is give or take 1 unit, you're going to have to take 13 samples of that poor guy. Not really keen on that, because blood samples are a pain, as I can vouch for. But evidently that's how many they need if they want to be sure, within give or take 1 unit. Are we good? Don't have any thumbs up today. We good? Yay, I do. I hope you're beginning to see, at least for this section of homework, that they really are just, they've got a theme, and it's find upper, lower, and all that good stuff. So in this question here, can you see upper, lower margin of error? That question is so standard now, you should just say normal, and sigma is known every time. 95% confident, that goes there. And I've forgotten what our number was. I think it was 13 or 14, whatever it is, it goes there. Right, let's look at this one. Total plasma volume. In determining the required plasma component in blood replacement therapy for a person undergoing surgery. Not quite sure what that is, but evidently it's something to do with your blood. Plasma volume is influenced by the overall health and physical activity of an individual. So suppose a random sample of 40 male firefighters are tested. Okay, so N is 40. And their average plasma volume is 37.5, some units I don't care about, and that sigma is 7.2. And they are asking us to find ZC for a 99% confidence interval. Okay, and then they want us to do an upper, a lower, and a margin of error. I won't do this question in entirety because I think we've done virtually the same question twice already. At least set it up. What's the magic C value if you want 99% confidence interval? Who do you use? %99 confidence interval. Who do you use?
Um, 2.58.
Yeah, wasn't meant to be a trick question. Right, that one. Right, the next bit I'm not doing, but we can at least finish off with the formula. Want to be X bar plus or minus 2.58 times sigma over root n. In this case, X bar, oops, I'll need to do a new line now, 2.58 times 7.2 over the square root of 40. So that's going to be what, 37.5. Ah, to heck with it, I've done it now. Might as well finish this line. So 2.58 times 7.2 divided by the square root of 40. And I am looking at, give or take, 2.9 to 1 decimal place. And so you take that number away from 37.5, so I guess I should do that. 37.5, take away 2.9, you get 34.6. That's the lower one. You might get the upper one, then you add it. That's 39, 40.4. And the margin of error is 2.9. So we can be 99% sure that, at least for firemen, that the total plasma level is going to be somewhere in that range there. So bigger than 35, but less than 41. Are we cool on that? We're good. So to finish with, as the sample size gets larger, what happens to the margin of error? Does that make sense? The bigger the sample, the error, right? The error shrinks down. Suppose you take a confidence interval, you go 80, then you go 90, and then you calculate it with the same data at 95, and then you go and you finish with the 99 point, I think it's 99%, yeah, with the 99%. So what happens as the confidence interval gets larger? What happens to the margin of error? If I get an interval at a confidence level of 80, it's kind of that size, right? Imagine a number line, like from there to there. And I'm 80% sure that the right answer is there. If the sample size stays the same and everything else stays the same, and the only thing that gets changed is the confidence interval. Well, if I want to be 90% sure, don't I have to make my interval bigger? You know, isn't that red one more likely to be right more often than the blue one? Right? I'm going to capture the right answer inside it. For intervals to get bigger, as they are here, the margin of error also gets larger. And we have some questions where they say, what happens if n gets larger? Does e get smaller, or does e get larger, or does it not matter one way or the other? And that is everything that we have that we need to cover in 7.1.